Hey guys, and welcome to Functional Print Friday, and welcome back to my shop. So before we kick off this week, I want to tell you guys a quick story. At some point in time here, I started setting my coffee down on the workbench before I say hi to you guys, and now I kind of feel obligated to do it because that's just how we start the video. But there's actually a story to this coffee that I want to tell you about. So I can't tell you when I started drinking coffee, but I can tell you for the last 10, 15 years, I typically have, probably like 3 cups of coffee a day. And I used to drink Keurig coffee. I used to drink, I think it was the Newman's Own K-Cups, and they were okay. They weren't great, they weren't bad. For K-Cup coffee, it's probably some of the best stuff. But I would put milk and sugar in it. And occasionally we'd go out to eat, or I'd get a cup of coffee from a decent coffee shop, and the coffee was so good, because I'd always try my coffee before I put anything in it. And occasionally I'd have a cup that was so good that I didn't want to put anything in it. And one day I became like obsessed with, I'm going to find good coffee that I don't have to put milk and sugar in. Because if you're drinking 3 cups of coffee a day, that's 3 times a day you're having sugar that you really don't need to be having sugar. So initially I had found this place in a farmer's market not too far from us, and I was buying coffee from them, and that worked out for a while, but then they stopped carrying the blend that I liked, and also it wasn't always the freshest. It was usually pretty fresh, but then other times I'd get a batch that was kind of stale. So I thought, all right, maybe I just need to find a place that will reliably get me coffee that's reasonably freshly roasted. So I came across these guys, and there's no sponsorship here. These guys have no idea that I am doing this. I'm just so happy with this company that I wanted to share it with you guys. So hopefully they're not actually upset that I'm sharing their brand here in the video. And I'm also not saying, hey, go out and buy this coffee or even from this brand. I mean, these guys are great. They are in Frenchtown, New Jersey, so they're only about an hour and a half from me. So their stuff also ships to me really fast, even just ground shipping. I imagine they probably ship all over the U.S., although I don't know. Check their site. The point is, though, if you are the type of coffee drinker that you like black coffee if it's truly good coffee, but you're drinking some other junk every day that you're putting milk and sugar or even worse, cream and sugar in, go find yourself good coffee. Okay, I promise, I'm really not going to talk about coffee anymore. So on the workbench this week is a project I've actually been working on now for a couple of weeks. And originally you guys were not going to see this because I thought it was going to be primarily a machining project. I did prototype all the parts with 3D printing, but the final parts needed to be machined, and I wasn't going to share it because I know you guys are here primarily for the 3D printing stuff. I'm as passionate about the machining stuff as I am 3D printing. Really, I'm passionate just about designing and making stuff. 3D printing is the right answer probably 85% of the time, and that's why I've got always plenty of content to show you guys. But I bought one of those arm systems that lets you hold 3 monitors off one pole for your desk, and I didn't actually realize it when I bought it, but my monitors do not have the standard, or well, 2 of my monitors do not have the standard Visa mount on the back. Like most monitors have 4 screw holes sort of roughly in the center that is a standard Visa size. And my 2 side monitors did not have that. Instead, they only mounted via this flat plate on the base. I've got 2 monitors that have this style base, and there's like a small metal plate that comes out of the bottom of the monitor, like almost all the way down at the bottom of the screen, that just screws on to this basically. So I kind of thought I could get away with, and I'll show you guys, I'll put some B-roll footage here on the screen so you guys can see what the end of the mount arm looks like, but this emulates the end of the mount arm. It comes to like this point, and I had initially made the assumption that this would be, I hadn't actually mounted it to my desk yet. I was sort of just putting everything together on the bench, but I made the assumption that this would be level, like in this direction, at the end of the arm, and this direction as well. And I thought I could just get away with this scrap of aluminum that I added some holes to, and I had just a spacer piece in here, and I added another hole in the metal mount for the monitor in the center, and I just put 1 beefy bolt through and figured I would be good to go. And this was a quick, easy solution. Yeah, that ended up not being the case because the end of these are not straight or level at all, depending on where the arm is articulated to. And yeah, I'll put a picture here. You guys can see how off that thing is. It's just about impossible to use. In fact, actually it looks better there in the picture than it is in person. So of course I came up with an overly complicated way to resolve this, and that is, so if you look at, this is the mount that's intended to work with this. So it ended like this, and there's just a bolt that goes through there. And then You get this motion, you get the up and down motion, which we also have built into the monitor. That little metal plate that goes onto here actually has a couple of degrees of swing back and forth. So I don't need that tipping motion, but this also rotates on the end. And I didn't actually even realize that it did this when I first got these. It's really stiff. I don't know if I can. Let me grab a wrench. Okay, so when the monitor is mounted to this, you have the leverage of the monitor, but you can see that this guy does twist on there. And I think that's why I didn't even realize that it twisted, because it's not obvious that it does. I thought they just had it riveted on there. But no, that turning action is actually quite important to make sure that you can level your screen. So what I came up with to solve for this was I emulated sort of the same shape that they had here, so that we get this rotation. And, you know, I had that with this block in here too. But what I needed to do was add the ability to turn the screen. So you notice this, these two faces out here and this hole. This then mounts onto here. Bolt goes in the end, and you loosen that bolt up, and then you can turn this piece, tighten that bolt up, and it will stay in place. And we have a flat face here that is essentially equivalent to this face here. And it'll use that same hole that I already drilled in the center of the steel bracket on the back of the monitor. So I can go this way. I can go this way, and then the monitor already has a couple of degrees tilt built into it for the other direction. Problem is, this is not going to be strong enough in plastic, or at least I don't trust it. I don't want my monitor falling off down onto my desk and breaking, so I figured that's no problem. I will machine these pieces in aluminum. Now mind you, this took about, I don't know, maybe 30 minutes to draw up this design, and then maybe 40 minutes to print these pieces. And then it took about 16 hours, yes, 16 hours to make these pieces out of aluminum. And it was fun. And, you know, I'm not an experienced machinist. You know, an experienced manual machinist probably could have made these faster than that. But there are a lot of faces here to machine, and a lot of precision bores as well. Obviously, this bore here needs to be the right fit to rotate on here without any slop. We have the four faces, the four flat faces back here, so that this can fit inside here. And this is a, yeah, there we go. So you can see how that goes together. Then this is a specific depth here for this bolt. This is drilled all the way through. It actually intersects with that hole there, and it's threaded inside of there so that we can tighten up this bolt. And then we have a threaded bore up here on the top to mount to. And mind you, I made two of these. One of them is actually already up in semi-use right now, which I will show you. And it's working great, with one exception. If you notice, these are not done. Notice a difference there in these pieces. And also, of course, you know, I'm obsessed with trying to do things as precise as I can. So I probably could have cut the time I spent making all these pieces in half if I did not try and shoot for, you know, within half a thousandth on every measurement, because that's really not necessary for a project like this. But I did. I think I managed to hit most of the measurements within a tenth. One of these, I think I went over on the depth or something. Some face I went over by like 2/1000ths, but it didn't affect the operation of it. But why are we here today? Why am I telling you about this? Well, if you notice again, these are not done. This piece matches this piece perfectly. All of the machining here is done. This piece is ready to go. However, this piece is not. You notice it's missing that round over. Now, I could just walk over to the sander and eat that material off with the sander. I could probably even roughly draw the shape of that, maybe bandsaw off the ears, and then smooth it on the sander. But you know I'm not going to do that. You know that I want it to be exactly as I designed it. And I mentioned I have two of these. The other one's actually already up and installed, because this does fit in here as is, but I can't turn it. So I can't get the arm exactly where I want it, because rather than being like here, I really want it to be like here. I want to move the articulated arm in the back to a slightly different spot, but I can't do that. The flat face is hitting here. I need that clearance here to be able to rotate this. So let's go up. I'll show you at the back of the monitor where I do have one of these installed, because we're also going to need to take that off to finish this out today. All All right, so back at the workbench, why are we here, right? Why is it that 3D printing is going to come into play at this point, since I told you that these pieces needed to be machined out of aluminum to be strong enough? Well, it's work holding. And you guys that, if you do any hobby machining today, particularly if you get into, more advanced machining like this in a manual fashion, because, if these were CNC, these probably would have been done in 5 minutes. Maybe I'm exaggerating, maybe 15 minutes, but it certainly wouldn't have been the 16 hours that I spent making 4 of these. But work holding is where you spend probably 3/4 of your time in machining. It's kind of like painting. If you've ever painted a room, especially if it's a smaller room, you spend more time prepping to paint, getting the paint all set up, and then cleaning up versus the time you actually spend painting the walls. Well, it's kind of the same with machining. You spend a tremendous amount of time work holding, figuring out how you're going to hold something and what cutter you're going to use and everything else associated with it. The actual machining, where you're removing material with a sharp tool, that goes real fast. So I left this face, or this feature, this curved feature out here, to last for 2 reasons. First reason, I couldn't think of a way to work hold it even when there was more to this piece. Even when there was more material here, I could have potentially held it when this was a bit longer in maybe even a V-block, but then I couldn't think of, if I was to finish the features out here, how I would hold it to finish the precision bore and the precision features that I needed out here on this side. So I've now kind of worked myself into a corner where I need to machine that last feature, but I have no way to hold the part. And that's where I think 3D printing is going to save us. And if you're also wondering how it is I'm going to get this nice sweeping curve here without a CNC, I've got something for that. I'm going to bring it over. Okay, this is a rotary table. Let me move the camera down so I can lay this guy down on its side, because it's actually got to hang over the edge of the table, and I'll show you how this works. All right, I bought us a little bit more space to work with here. We can hang the handle over the edge of the table. Now, if I stand it on that back face, it does actually clear. And if you own a rotary table and you're wondering how it is that I'm doing that, since normally this handle just will not clear at all, regardless of whether it is on the angle face or the flat bottom, I actually, here, let's slide this over the end. This thing's really heavy, by the way. But I actually added a 3D printed riser piece here. This is not to use, this is not for use, while on the milling table. This just raises this up enough so that I can actually store it standing up without the crank here hanging lower than the bottom of our precision face here. So if you happen to own one of these Vertex 8-inch rotary tables, I'll make sure this STL gets in the zip file for today's designs. All right, so now that this is flat here on the table, and this is how it'll be mounted on the milling machine, if I grab our piece here that we need to mill this round feature, you can probably start to guess how this is going to work. So imagine, let's see, so imagine our part is somehow held stationary to the round table here. Our bit is in the spindle of the milling machine, spinning real fast. It's stationary. And sorry, I need my other hand here. So just imagine that end mill is still right there. As I now rotate this table, the work itself moves relative to the end mill and should cut us that nice curve there. The challenge still is, how on earth do we hold this piece to this table securely? And the idea I have is to design a jig that's 3D printed that will mount down to this table to hold our aluminum parts. So it's not going to hold that one. It's going to hold this one. And I think we're also going to need to machine some sort of plug here in the center. I think this is a Morse taper. I believe it's Morse taper 3. So we'll have to see if we can modify a Morse taper 3 something that'll drop down in that hole and give us the ability to line up on this center bore, because that's what we want to be lined up on. This, we can measure the distance between the center point of this bore and the center point of where the correct size end mill is going to be to cut this curve here. So yeah, I guess this is technically still going to be both a machining project and a 3D printing project. But the bigger challenge is going to be designing something to hold this part securely. All right, and here is the design that I came up with. The general idea is that I've got a thick plate here we'll probably just do this in PLA. PLA is nice and rigid and it is cheap. That mounts with studs down to the T-slots and holds our part perfectly in the center. And we're not really relying on our fixture here to keep this centered. Remember, we're gonna have something that actually sits down in the taper here in the rotary table and has a pin that comes up. So essentially we'll set this down over top of that pin and then bolt this in place. And then we'll know that we are actually in the center. And here, if I, let's see, if I hide this, you can see we don't have a whole lot to hang on to. Just as a reminder, the part itself is very short. So if I bring this back, and here I'll explode this. I think if I knock this top face off, it's probably easier to understand what's going on. There you can see we have 2 bores here for our part to go into, and that should give us good holding power because we need as much surface area essentially as we can get. That does not get in the way of the cutter that's going to sweep around here to create this shape. And I think as long as we have a nice tight fit on both of these bores, we should be good. And then we'll draw that part into the fixture through the back. Because remember, this part itself, it's not actually depicted here in the drawing, but it has a hole that goes all the way through into this bore, and that's threaded M8. So we can put an M8 bolt in from the back to draw this guy into the fixture. So, all right, I'm gonna print this out and let's see how everything fits, and I'll bring you guys back. Okay, our first draft of that design is printing, and I found the right piece to order for this, and that'll actually be here tomorrow to machine down. It's basically, I found an arbor that is a Morse Taper 3 and a machinable arbor, and we'll end up actually cutting most of that arbor off just flush with this table, and then we can center bore it. I'm pretty sure I have an adapter that goes in the spindle of my larger lathe that goes from, I think, the Morse Taper 5.5 that the spindle is to Morse Taper 3 that should hold that Morse Taper arbor and let us actually machine directly at the spindle. But while we're waiting for all that, if you caught the videos from last week and the week before that, we did a bunch of material testing. It was mostly around TPU for AMS. If you missed those videos, go check them out. But one of the things that I saw in the comments that caught my interest was we ended up doing the final design in PETG HF. And at least one person said, you know, I think PETG itself is actually a lot stronger. And I actually had some plain old regular PETG, so I made sure it was completely dry, and I printed out some test pieces for that too. So let me just pop these in the vise quick, and let's see how these compare to PETG HF. All right, so same setup as last week. I've got the first test piece here in the vise, and we'll use the larger of the 2 force gauges since I expect this to be over 10 kilograms. I don't actually remember what the PETG HF was, but I'll go look that up in last week's video, and I'll put both numbers up on the screen after we test these. Okay, that first one was 15. I don't remember pushing that hard last week, so I'm pretty sure that was higher, or at least the first test piece was higher than PETG HF. I braced myself a little better for this one. All right, that one broke a little bit easier than the first one, but I think averaged out, that's still going to be higher than PETG HF. You guys are seeing the numbers up on your screen now comparing the two. All right, our first test piece is done, and this pretty much looks like what I had in mind, although the screw holes don't look square on there. I think I may have made a mistake in the design. I think these are closer to the edge. It's funny, it's the things you notice when you're holding the part in your hand that you don't notice when you're looking at the 3D view on the screen. But I think we could probably still test this on here, I think. I also ordered 2 of those arbors that I was talking about. This is, you can see it's just a Morse taper down here and then a machinable steel arbor up here on the end. The idea being that we drop this down in the center and machine it until it is flush with the top of the table, and then have a bore in the center. And this is actually the second one. I bought 2 of these because I thought I might screw it up. And the first one is in fact already done. So we can test that as well. We should, if everything is good, and let me clean this really well. Since this is precision ground, I want to make sure there isn't even any little dust particles in there. Otherwise it is not going to seat correctly. All right, that is perfectly flush with the top of the table. And I actually already went and made up a pin in the correct size. And look at that. Look how good that fits in there. It even does that little slow motion sort of drop in place as the air comes out of the board. That's a satisfying fit. So if this works as designed, we should be able to fit this piece in here. I think I see a second mistake I made. Okay, yeah, so the second bore is tight. There's two bores here. There is, in our 3D printed part, there is the bore for this diameter and the bore for this diameter. The bore for the smaller diameter must be a good fit because it's, yeah, that pushes in really nice, but I can see we have a gap on the outer bore. Not much, maybe half a millimeter. So I must have measured that wrong. Or I just didn't translate a number correctly. We're going to need all the support we can get. So we're going to need to do a revision with that bore adjusted. And like I said, I don't think these holes line up correctly either. But let's just try this. So we should be able to drop that down. Yep. So if we put the table on the milling machine, we center up on the bore here first so that we position the spindle of the milling machine directly over that hole. Then we drop our pin in. And then we center up our part on top. We know that the bore of our part right here is exactly centered underneath the spindle on the milling machine. And then we can just move the specific distance out to cut that rounded feature on the end. So that should work. I think we have enough clearance here without getting into the plastic, but that's the nice thing about 3D printed fixtures. If we cut into it, it doesn't really matter. I mean, this is probably like $1 worth of PLA. So, all right, let me go make those revisions. I'm not even going to try and bolt this up because I think we're going to be, yeah, I think these two are going to be too close to the end here. I don't think we're going to get the T-nut under. So let me make those revisions and I'll bring you guys right back. All right, our second version is done. And I also increased the diameter of these holes a little bit just to give us a little more wiggle room because I realized that we might not end up within just the span of how much here. Let me get this out of here. Actually, yeah, before I even put the piece in. So I'm expecting, if everything in the design is just right, that these 4 holes will line up exactly within these T-slots when we are on the center of the bore of this piece. But in case we're not exactly precise with that, it doesn't really matter as long as we bolt this down in the right position. So I increased these to just give us a little extra wiggle room on the studs that we're going to use to mount this down. So let's see if this all fits now. Oh yeah, actually that fits really, really nice. If you guys can see on the camera there, that is, we are right on that bore now. And the inner one I think is a nice tight fit too because, yeah, it snugged up before I dropped it in. Before we hit that second bore, it was already nice and snug. So, all right, I'm going to need to make up a quick spacer for the back here. I left this room for a long bolt in from the back since this is already threaded. That'll pull this piece back into here. But I don't want to clamp against the 3D printed surface. I want to make an aluminum spacer so that that force is spread nice and evenly across there. If we just use a washer, the washer is going to bend and we're still not going to distribute the force. But if we make ourselves like a, I don't know, like a 5 or 10 millimeter thick aluminum spacer, we should be good. And I'll have to check the bolt length too, because whatever length I make the spacer needs to allow us to tighten up without going into this bore. If the bolt goes into that bore, we can't use the centering pin. So I'll bring you guys right back. All right, our spacer is done, and I'm really glad I thought to think about the length of the bolt, because if I went any thicker than this for the spacer, we wouldn't have enough thread engagement on the longest bolt that I had in the correct size. So it should tighten up in there really nice. Let me grab the right Allen key. All right, I guess we don't actually want to snug that up yet because I don't know yet if this is exactly straight in here. Our pin will get us close. But I'll probably sweep back and forth across this with an indicator once we're up on the milling table before I tighten that down. So we're ready to go. I'm just going to make it straight by eye for now. It should drop over the pin. I guess I've got to make sure these surfaces are nice and clean. Okay, I think that's going to work. I'm going to go grab the T-nuts and the studs and flange nuts, and let's see how this bolts up. All right, well, there's no point in making these more than finger tight because I'm going to have to take this back off to center up the table once we put it up on the milling machine. But so far, in theory, this looks like it is really nice and snug on there. If I just, let's see, if I just make these finger tight and we tighten up our bolt here on the back. I mean, I can't feel any movement in our part at all. I mean, we probably shouldn't take really heavy cuts on that, but I think it's going to work. And I'm really excited about this because work holding in general on rotary tables is really hard. Just because you have a limited area to work in. And this is a 4-slot table. A lot of them in this size are 3-slot tables. So getting your part up there and figuring out something that works with spacers and strap clamps is often really tricky. I think we might be able to copy and paste this type of solution to a lot of work holding that comes up here on the rotary table. In fact, I've already got another idea in mind that maybe we'll tackle towards the end of this video if there is time. But let me pause here. I'm going to get this all set up on the milling machine, centered up, and ready to go, because that's going to take a while and it's boring, so I'll bring you guys back. All right, guys, I'm back. I think I've got everything set up here correctly. I found the center of the rotary table. I zeroed out on that, mounted a piece up here, centered the piece, or really set this down on top of that pin, and then bolted this down in place. I indicated the rotation of our part in there, and then I indicated in the rotation of the rotary table to make sure that one of these faces was straight with the axis. I think we're ready to go. I am super nervous about doing this. If we scrap this part, it is a lot of work to remake it. On top of that, I've never actually used this rotary table. This will be the first time that I'm using it. So yeah, I'm gonna get you guys in the tripod, and I think what I'm gonna do is try and just do a skim cut on the top. This rotary table rotates 360 degrees with 90 turns of this handle. We wanna go halfway around, so we wanna turn this handle 45 times. I've got it zeroed out here. So I'm gonna go clockwise 45 times and come back to 0, and then this should rotate around and the cutter should be on the other side. I've set my cutter distance based on this, just visually, so I could for sure understand what's going on here. The relationship between the 0 point of the center of the rotation of the rotary table and the center of the cutter, it is a 7/16 end mill, is 18.40625, and the closest I can get here on the DRO for the milling machine is 18.405, which, I mean, you know, we don't need that level of accuracy anyway. And that does jive with the cutter looking like it is in the right place. If I bring the quill down, it just kind of kisses the side. So I'm pretty sure everything is all set here. So, all right, I'm gonna get you guys in the tripod. I don't know how much of machining I'm gonna show because I don't know if I'm gonna be able to find a spot that the camera can even see this real well and not be in the way of me trying to do this, but I'll bring you guys back. I think that looks right. That was 45 turns on the handle. It looks like we're starting and stopping in the right place. We're probably not going to get a perfect transition, but should be pretty close. So, all right, I don't know how much depth is safe to take here because remember our fixture is just PLA. So this is probably going to take a bit. I'm going to get you guys back in the tripod and I'll just speed this back up. All right, guys, I'm down to the bottom of the part. I'm not going to sugarcoat it. This one came out pretty poorly. I made a number of mistakes here. I did 2 passes at 2 millimeters, then I did a 3 millimeter pass, and I thought, you know what? If I turn the RPMs up, I can probably go full depth and maybe get a cleaner cut. And I didn't consider that if I do that, I'm going to build up a lot of heat in this part. I think that's exactly what happened. I think it got hot. I think it actually pulled in to the PLA a little bit. I think it heated up. Remember, we've got that bolt back here pulling tension on it. I think it pulled it in a little bit because if you look, our depth of cut relative to the circumference here has actually decreased by probably, it's probably 2 or 3 thou. I think we can still salvage this. I think if I loosen up these flange nuts, I think this guy is going to want to naturally recenter on that pin. I think right now the part has pulled into the PLA by a couple of thou due to it getting hot and softening up the PLA. So that's what I'm going to do. I'm going to loosen these up. And the next one, I'm not going to try and do a full depth cut. I also, if you saw me, when I brought the vacuum over, the vacuum isn't just to evacuate the chips. It also cools the part. Pulling air over the part cools the part off. And plunge cutting, I had a lot less cutting force. So I think the next one that I do, I'm going to not go the full depth. I'm going to plunge out the majority of the part, then set my depth to be, well, when I say depth, I mean depth to from the position of the cutter to the center axis of the part. Then do 1 full rotation and make it in 1 cut, which should clean up really nice. The reason the surface finish is garbage is because, well, I think the reason it's garbage is because we're recutting chips. It could also be that our fixture here is just not rigid enough. But I don't think that's it. I think the bigger part is that we're recutting chips because I was doing those just like the 2 millimeter depths of cut and just the chips were kind of piling up in there. So let me see if I can salvage this one and I'll bring you guys back. All right, I increased the depth of cut just a little bit, which means we're going to have a little bit of cleanup here on the sides just to blend in, but I think that came out pretty good. I think we kind of lucked out on that one, and I definitely learned a lot that I'm going to apply in cutting the second one. Honestly, the surface finish on the bottom portion is pretty good. It's just at the top there, I don't know if it's because the part moved and I still never got back to that original depth or what, but I can still feel a small step there. So there's still going to be some cleanup to do. That may also just have been chips getting in there and getting recut. When I did the finishing cuts down here, I did put some WD-40 just to lubricate it. I think that was a combination of recutting chips and the chips sticking to the end mill. But let me get this out. All right, so here's our part out of the fixture. And I gotta say, the bottom 2/3 is really nice. I think our fixture is plenty rigid enough. There is no way that we would have gotten a surface finish that good on the bottom 2/3 if that guy was chattering around in the fixture. Yeah, I'm really happy with that. I'm going to clean this up on the sander, and I think we could probably install this one. All right, guys, I think that cleaned up pretty darn good. Is it perfect? No. And you know my eyes know where all the little tool marks are in there, but I think it looks pretty darn good, especially when you consider that we held that in a 3D printed fixture, and that was my first time using a rotary table, so I'm pretty happy with the result that we got. I'm going to go install this, and I'll bring you guys back. All right, wanted to give you guys a quick look before I actually slide the monitor back on the mount here because it's going to be a lot darker behind the screen. But that's what it looks like, and you can see we have the adjustability of swinging this back and forth, and then we can loosen this bolt here in the front to rotate the monitor. Yeah, what a difference. It'll be really nice to actually see all 3 screens later on when I'm editing tonight's video. And even though you can't see it from the angle that you sit at here at the desk, if you come down level with the front of the screen, you can see that you can access that bolt in the front to adjust the rotation of the screen. All right, so I mentioned earlier in the video when I came up with this idea that I think this is just sort of the tip of the iceberg, this fixturing idea on the rotary table, if this works, because again, it's so hard to hold parts on the rotary table. And just as an example, let's say we had some funky shaped part like this. Now, this is not actually a part. This is just a scrap out of my pile, but it illustrates the example that, you know, this is also going to be really hard to hold on to. I guess we could kind of try and screw it down from the edges to a spoil board maybe and mount the spoil board to the rotary table, maybe. I don't know. It might still end up in the way of our cutter because let's say we want to cut like a slot in this guy. This is another type of operation you typically do on a rotary table. So maybe like a slot in this guy like this. All right, that looks like a really sad banana, but you guys get the idea. So to cut this, this part would rotate around on the rotary table and we would cut that slot. So what I did was, it took me a couple tries to get it just right, but I scanned this part, turned it into a DXF, and made just a test piece here that this drops into. You guys probably already get what I'm getting to here, because much like this part, I have one here that has that same cutout in it, and this will drop in. Actually a little bit tighter fit in this one, but I think it'll go in there. I think I didn't tune this filament, and I have a top to this too, and this one's 3 different colors. You know, I've got so much old filament that, you know, I've got like, say, 1/3 of a roll or 1/4 of a roll of something, and I don't plan on stocking that color. Like, it's not filament that I'm gonna buy again, and some of it is, like, actually this gray and probably this green, not the red. The red I probably bought within the last couple of years, but this green here on the top and this gray I've probably had for 5+ years. And I thought, you know what, I'm just gonna start feeding it into the printer for functional parts like this that are like single use or that the appearance doesn't matter. Or test parts, like, you know, for example, this one. I didn't expect this first try to work, and we're not keeping this around anyway, so this could, even if this was the final version, there's no reason that couldn't have been printed in half pink and half yellow. So you're probably going to see more mixed colors like this on the channel just as I use up some of my old rolls of filament. But I think you guys get the idea here, right? So, and in fact, to visualize this better, I even have a test piece here that illustrates what I'm trying to do that has the slot already cut in it. So this circumference obviously goes around our center here, and this is 8mm, just the same as the aluminum piece that we had. So this will sit down over that pin on the rotary table. This will clamp on top like this, and we should be able to go in there with an end mill, cut that slot. Now, I'm not going to center everything up for this one the same as I did for the other because this is just a test. I'm just going to eyeball it. We'll know if it works, and I don't see why it wouldn't. I mean, sure, this is just PLA, but all the cutting forces are going to be trying to pull this guy like in this direction or this direction. Or this direction or this direction. It's not like it's going to be trying to lift this apart, and I don't think it would come apart anyway. This is, you can see better from the bottom. I printed all this with 6 walls and gyroid infill. I mean, the infill doesn't matter that much, but 6 walls on this, and this thing should be plenty strong. So let me go get this on the table of the milling machine, and let's try this one out quick. All right, I ran into a couple issues there. The first one was the table locks actually hit the T-nuts if I have the T-nuts this far out in the slots. So I'm either going to need to modify a set of T-nuts so that I can use studs this far out in the T-slots, or I got to just move the holes here inward a little bit, which I would prefer not to do because then that limits the amount of work I can do on the table. I guess I could also, if I made this even thicker, just have this recessed, these recessed below the surface as long as they weren't in the area that we're going to cut in. And I also don't have an end mill in this diameter that is long enough to get up close enough to this flange bolt to be centered here in our relief area. So we'll be a little bit off center, but that's okay. I mean, I just eyeballed it anyway. This is really just to kind of test it, proof of concept to see if this does work. So let me get you guys back in the tripod. Let's give it a go. All right, well, if I was really thinking, I would have put some holes all the way through so that we could push the part out from the other side, because of course now it is it's stuck in there. And we probably have a combination of aluminum chips and melted PLA here. So yeah, how am I gonna get this out? Huh. Give us a quick deburr. Well, honestly, it came out pretty darn good. I think I would probably use the vacuum or some compressed air just to keep the chips out of there. I can see the surface finish actually inside there is pretty bad in places because the chips were recut. But yeah, I would say that totally worked. Well, guys, I'm really happy with the results that we got here. You know, if we were doing a production part, obviously I would have taken my time more with this, but this is just a proof of concept. Really, I honestly just made this one to show you guys kind of what I was thinking about for this rather than try and just explain it. This is the one I was really, really fingers crossed that it was going to work. I knew that there was a chance that this was just not going to be rigid enough for the cutting forces. Now, you know, that was an aluminum part. Could we have done it in steel? I don't know. I think so. It didn't seem like at any point in time we were anywhere near the rigidity that we could get out of this fixture. Yeah, it did get a little hot and the part pulled in a little bit. The bolt just pulled it in a little bit. You can actually see a little bit of plastic that kind of squeezed up inside there. But it stayed true. So I just have to remember that the next time I do something like this on the rotary table that I keep the part cool. You know, either use the vacuum, compressed air, a little bit of lubricant. But yeah, I mean, I'm calling that a success. Guys, as always, thanks for hanging out in the shop with me for this week's designs and prints. It really means a lot to me, you know, to see the comments on these videos and to be able to share this with you guys. So, you know, as always, if there's anything that you would have done differently, or if this gives you any ideas to how to kind of extend this idea, please let me know down in the comments. I do read all the comments. I don't get an opportunity to respond to every single comment, but I do read every single comment that you guys leave me. And if this is by chance your first time here on the channel, this is all we do. It's all functional prints. A lot of stuff out here in the shop, but I do stuff out in the yard and around the house as well. So if you're into that sort of thing, check out some of the other videos on the channel. And if you like what you see, guys, hit that subscribe button. And if you do, I'll see you next Friday.